Finite element analysis is a very important tool set for the design engineer who is designing products. Many times design engineers do not delve into the deep mathematics of FEA, finite element analysis, but they should know what is the underlying principle in FEA and how to make sense of the results which are being shown, and to make sure that the output which we are getting from the FEA is meaningful for our design or not. For that, we need to at least understand the fundamentals of the FEA workflow. So in this video, I will try to simplify the underlying principles of the FEA workflow.
The first step is always to define the problem. What are we dealing with? Let's say, for example, if you're having a bracket which is rigidly attached to a frame and that bracket is taking a load. For example, let's say if you're designing an engine mount bracket in a frame, in a chassis frame. So that engine mount bracket is attached to the frame, the chassis frame rigidly, and it has to take the load of the engine. So we need to specify the geometry, which is generally specified as a CAD model. The bracket CAD model is generally specified as the geometry. And then we need to specify where the loads will be applied on that bracket. So what are the areas on which the loads will be applied? What will be the types of loads? And will there be any separate load cases, that is vertical load in one case, horizontal load in another case, or combined loads? So the load cases have to be known. Then what are the boundary conditions or constraints we need to apply to that model? So let's say if you are having a bracket, how is it attached to the frame? Whether it is welded to the frame or whether it is bolted to the frame, how it is attached to the frame. So based on that, the nodal constraints which have to be applied on the model are decided. And then of course the final one is the materials, the material profile of that bracket. What is the material made of? What is the mechanical properties of that material? The Young's modulus and all of that have to be input. So these four inputs will define the problem in a holistic way, and then from that only everything else originates. The next step, the step 2, once we have the geometry, once we have the understanding of the loads, the constraints and the materials, the next step is to discretize the geometry. So to discretize the geometry, to convert the geometry into sub elements which can then be analyzed at the element level. The discretization is an important step which is generally called as meshing. So in finite element analysis it's called as meshing. So it is basically discretization of the geometry into elements and nodes. So at this point we need to select the type of elements which have to be used and the number of nodes for each element and the definition of those elements in terms of the size of that element. So all of that has to be decided at this point when discretization is to be done. Then once the discretization is done, the element level matrices for force and displacement vectors are generated for each and every element. So the element level matrices for force and displacement vectors, as we had seen earlier, which we had a cantilever beam in which there are two elements. So like that, let's say if you're having a bracket and it has, let's say 1,000 elements. So for each and every one of those 1,000 elements, the force and displacement vectors are generated based on the boundary conditions and loading conditions which have been applied in the input. So the matrices are developed and then the boundary conditions and loading conditions are applied. And as we had earlier seen, some values might become 0, some values might be known with a input of the loads, or some values will be unknown, while most of the values will be unknown. So developing the element level matrices for force and development vectors is the next step. And applying the boundary conditions and loading conditions on them. Next step is to derive the stiffness matrix from the differential equations for the elements which have been used. So the differential equations are solved to develop the stiffness matrices for each element. The stiffness functions are functions of material properties and geometric section properties. Just generally the stiffness functions, as we had earlier seen in the case of the rod which was loaded axially, it was AE by L. So it was a function of geometric section properties and material properties. Geometric section properties include moment of inertia, length, area, etc. And material properties includes Young's modulus. So the stiffness functions which are derived are generally functions of these two, material and geometry. Now when the matrices for the element level, the force matrix, the stiffness matrix and the displacement matrix are developed, now these matrices have to be assembled to get the global stiffness, force and displacement matrices. And once the global matrices are assembled together, the solution will take place, or the solving will happen afterwards, and the matrices are solved and the unknown displacements and rotations of each node are found out. Now, after finding out the unknown displacements and rotations for each node, these displacements will give us the value of strain in the 7th step. So the displacements which we find out will give the value of strain, and from the value of strain, the stress can be calculated as per Hooke's law, considering that the material is linear in fashion and follows the Young's modulus. So this is a very basic overview of the methodology of finite element analysis. First, defining the problem, then discretization, then developing the element level matrices, and then developing the stiffness matrix using the differential equations, and then assembling the element level matrices in the global stiffness matrix, solving to find out the unknown displacements, and from the unknown displacements calculating the stress. Here is an example of a cantilever bracket which is loaded at the end as shown over here and fixed over here. Now the geometry is non-standard. As you can see, it has a variation in its section and it also has a cutout, and there are multiple curvatures associated in the geometry. Hence, solving it using the traditional method, classical method, will be very difficult. So using FEA is justifiable. So while we are using FEA, if we are selecting the element, the triangular planar elements, considering it as a 2D problem, we are considering this cantilever as a 2D problem, and we are using 2D triangular elements, triangular planar elements, which have 3 nodes. So the first step is to define the problem. So we are defining the geometry of the cantilever. This is the geometry, this is the loading. So that is a load applied over here, and the load is applied at the end. So load will be applied at the nodes at the end of the geometry as shown over here, and the load value is 2500 Newton, and on the other side all the nodes will be fixed. So these nodes 1, 2, 3, 4, 5 will be fixed. So this side will be fixed, and the material of the cantilever will be steel. So this is the first definition of the problem. We have defined the loads, we have defined the boundary conditions, we define the materials as well as the geometry. Now next is discretization. So this image shows one possible way of discretization of this geometry using the software. So this is a mesh which is having triangular 2D elements. All of these elements are triangular 2D elements, each having different geometries, as you can see over here. Now these nodes, this node, this node, this node, and this node, and this node, which are 5 nodes over here for various elements. These 5 nodes are fixed. So they are fixed. The degrees of freedom allowed to them is 0 for these 5 nodes. Whereas these 3 nodes, 6, 7, and 8 nodes, on these nodes, the load is being applied in the vertical downward direction in y-axis, which is a value of 2500. So on these nodes, 2500 Newton load is being applied. So now the step 1 and step 2 is completed, and using this data of the boundary conditions and the nodes on which the constraints are applied and the nodes on which the loading is applied, the force matrix and the displacement matrix can be generated. And using the differential equation which is associated for the cantilever beam, the stiffness matrix can also be generated for the elements. Once that is done, the assembly of all those element level matrices is done to get the global matrix. Then the global level matrices are solved, the equation is solved, and the unknown values, values of displacement of the various nodes which are free, which are not constrained, are found out. So rest all of the nodes apart from 1, 2, 3, 4, 5 are free to move and have all degrees of freedom available to them, which is over here 3 degrees of freedom because it's a planar element. So all of the nodes apart from these 5 nodes are free to move. Hence the displacements of all of these nodes can be calculated through the analysis, and this is the result. So this is the plot of displacement. This is the plot for displacement at the bottom, and this is the plot for the stress. So this plot of displacement shows that the highest displacement is at this node. That is this node. That is the point of highest displacement. And the variation field is seen over here. How it varies from the end where the loading is happening till the fixed end where the displacement is 0. And from the solved matrices which gives the displacement for each node, the stress is also calculated as shown over here in the middle picture. So the stress is maximum at this point, which is shown by the red areas, orange or red areas. So this is an example to showcase a simple workflow in FEA, how from the first step of definition of the problem, when we are defining the loads, the geometry, the constraints and the material, from that it goes towards the calculation of displacement and stress. So the FEA methodology has 4 major steps. First one is problem definition, second one is pre-processing, third one is solving, finding the solution to the matrices, and then the last one is post-processing. The first step of problem definition is the most important step. If the problem is not well defined or not accurately defined, then the results will not be meaningful. So the problem definition is primarily driven by the engineer, because the computation is done, the computation part might be done by the computer, but what has to be computed and what are the input conditions, input boundary and loading conditions, and what are the materials and what is the geometry, that has to be decided by the engineer who is performing the analysis. So problem definition is the most important. And once the problem has been defined, once the geometry has been finalized, once the material is known and applied to the geometry, the boundary conditions are applied and loading conditions are known, then the next step is to discretize. To discretize the geometry into the sub-elements, which is called as meshing, and to define the boundary and loading conditions based on the problem definition. So this step, pre-processing, is aided by computation. That is, we mesh a component using the computational power. And then after the pre-processing, once the discretization has been done and once the boundary conditions have been established and the loading conditions have been established, next step is to solve. Solving the differential equations and finding the approximate stiffness functions for each element, then assembling the element stiffness matrices in the global stiffness matrix, assembling the force moment vector equations in the global stiffness matrix, and assembling the displacement vector equations in the global stiffness matrix, and then finally solving the equations to getting the unknown displacements and getting the strain, and in turn getting the stress values. So all of this is done by the computer in the computation phase, or called as solving phase. This is the third step in the FEA process. Next step is post-processing. Once the solution has been derived, the solution has to be visualized in a way in which we can derive meaningful outcomes from it. So post-processing involves plotting of the results in the form of graphs, and then manipulating the results in the way in which it gives us meaningful insights into the analysis. So 4 major steps. First one, the most important one, problem definition. Second one, pre-processing, where meshing, then discretization and definition of the boundary conditions and loading conditions in the mesh is done. Third one is solving, which is purely done by the computer, computation. And then fourth one is post-processing, where the results are visualized.